ever stop and think about what's actually going on inside your phone or your laptop? It feels like magic, but really, it all boils down to this incredibly clever translation. Today, we're going to pull back the curtain and decode the secret language of computers. We'll see how they take our world and turn it into something they can understand, using just two numbers. You ready? Let's dive in. All right, to kick things off, let's just pick a number. Something totally normal, a number you wouldn't think twice about. How about 58? To you and me, it's just 58. Simple. But to a computer, it's like a secret message. So what's the big mystery? How in the world does a machine see that number? Well, to a computer, 58 looks like this, 111010. I know, right? It looks totally random, like someone just mashed the keyboard. But I promise you, there's a perfect logic to it. And by the end of this, we're not just going to crack this code. You're going to know exactly how to do this translation yourself. Okay, first things first, we need to get a handle on the fundamental problem here, this communication gap between us and our machines. Honestly, you can think of it like a classic language barrier. I mean, think about our language. It's so rich, so complex. We've got 10 different digits, dozens of letters, all these symbols. We can express pretty much any idea. A computer, though, it's way, way simpler. Its entire world, everything it does, is built on just two states, on or off. That's it. We just represent those states as a 1 and a 0. So its real genius isn't about some deep understanding. It's about being able to process billions and billions of these simple ones and zeros at mind-boggling speeds. So how do we bridge that gap? Well, that's where this crucial idea called coding comes in. And look, when we say coding here, we're talking about the most fundamental level. It's simply the set of rules we've agreed on to translate our information, numbers, text, pictures, all of it, into those long, long sequences of ones and zeros or bits that a machine can actually work with. Now, here's the funny thing. Before we can really learn the computer's language, we actually have to take a closer look at our own. We need to crack the code of our own number system, a system we use every single day without even thinking about the rules behind it. Right. So we all use the decimal system. You might have heard it called base 10. And you probably think of it as just the 10 symbols we use, 0 through 9. But that's only half the story. The real magic, the real power, comes from this kind of hidden rule, an idea called place value or weight. Just look at a number like 4,567. We all know what it means instantly, but let's actually break it down, The 7 on the end, that just means 7 ones. Simple. The 6 next to it, that doesn't just mean 6, it means 6 tens. The 5 means 5 hundreds, and the 4 means 4 thousands. See what's happening? Each position, each place, has a value that's a power of 10. That's the secret sauce. And that core idea is what makes every number system tick. Okay, so if our system is base 10, what else is out there? Well, in the world of computing, there are 3 other systems that are super, super important to know. So besides our good old decimal system, you've got binary, or base 2. This is the big one. It uses only zeros and ones, and it is the computer's native language. Then you have octal, which is base 8, and hexadecimal, base 16. Now you might be wondering, why do we even need these? Well, just try to imagine reading a whole page of nothing but ones and zeros. It would be a nightmare. Octal and hex are basically convenient shorthands that make those super long binary strings much, much easier for programmers to read and work with. And check out hexadecimal. It's so cool, it even uses the letters A through F to stand in for the numbers 10 through 15. All right, we know the different systems, we know the players. Now for the fun part. How do we actually translate between them? Let's get our hands dirty and learn the rules. So, to get from our comfortable base 10 to any other base, we'll just call it base B for now, we use this really simple method called successive division. It sounds complicated, but it's not, I promise. Here's how it works. Step 1. You take your number and divide it by the new base you're going for. Step 2. You just write down the remainder. Step 3. You take the whole number part of your answer, the quotient, and you do it all over again. You just keep repeating that until your quotient hits 0. And the last step? You take all those remainders you collected and you just read them from the bottom up. That's it. Let's actually try it. Okay, let's go back to our mystery number from the beginning, 58. We're going to convert it to binary or base 2 using that method we just talked about. So first we do 58 divided by 2. That gives us 29 with a remainder of 0. Got it? Now we take the 29. 29 divided by 2 is 14 with a remainder of 1. We keep this going. 14 by 2, then 7 by 2, and so on, all the way down until we can't divide anymore and we get a quotient of 0. And now for the magic trick, we read those remainders from the bottom all the way to the top. And what do we get? 111010. See? The secret code is cracked. It makes perfect sense now. Awesome. So we can translate to binary. But what about going the other way? How do we translate that string of ones and zeros back into a number we can actually understand? Well, for that, we use that exact same place value idea we talked about with our own number system. It's a method sometimes called the polynomial form. Let's grab a new binary number to play with, 1110111. Now, just like in our base 10 system, every position has a certain weight, but this time, instead of powers of 10, it's powers of 2. So we just multiply each digit by its matching power of 2, starting from the far right with 2 to the power of 0. Then you just add up all those little products, and bam, the number in decimal is 123. It works perfectly both ways. Okay, now for the really cool part, the stuff that makes you feel like a pro. While those methods we just learned work for converting to any base, there are some incredibly fast shortcuts you can use for bouncing between binary, octal, and hexadecimal. And it's all because they're related by powers of 2. Check this out. To convert a binary number to octal or base 8, you don't have to do any of that division or multiplication stuff. The trick is that 8 is just 2 to the power of 3. So literally all you have to do is group the binary digits into little sets of 3, starting from the right. Okay, let's take this binary number, 10111010. Starting from the right, we group it up. The first group is 010. The next group is 011. Now that last one is all by itself, right? No problem. We just add 2 zeros to the front to make it a full group of 3, 001. Now you just convert each of those tiny groups into a single digit. 001 is just 1, 011 is 3, and 010 is 2. Put them all together and you get the octal number 132. How easy is that? It's so fast. And guess what? The exact same logic works for hexadecimal, or base 16. Since 16 is 2 to the power of 4, we just group the binary digits into sets of 4 instead of 3. Let's use that same binary number again. This time, we'll group it into 4s from the right. That gives us 2 groups, 1010 and 0101. Okay, 0101 is just 5. Easy. Now, 1010. If you work it out, that's the decimal number 10. And remember from our chart, in hexadecimal, 10 is represented by the letter A. So our number is 5A. This shortcut is exactly how programmers can look at a massive screen of ones and zeros and actually make sense of it quickly. So we've learned how to do all this translation back and forth. It's a neat skill. But why? Why is this fundamental skill so incredibly important? Because this isn't just some clever math trick. This isn't just for a test. This process of translation, it is the absolute rock-solid foundation of our entire digital world. Everything we see and use every day is just the tip of the iceberg. Underneath it all, supporting absolutely everything, is a massive, massive foundation of binary code. You know, there's this one sentence from our source material that just sums it all up perfectly. It says, coding consists of establishing a correspondence between the external representation of the information we use and its internal representation in the machine, which is a sequence of bits. Think about that. Every single email you send, every photo you snap, every video you watch, it's all ultimately being chopped up, translated, and stored as a gigantic sequence of these simple ones and zeros. When you understand this translation, you're understanding the very language of technology itself. And that brings me to one last thought to leave you with. Our whole digital revolution, everything we've built, is based on a simple two-state system, on and off, 1 and 0. It kind of makes you wonder, doesn't it? What new possibilities, what incredible new forms of computation could we unlock if our machines weren't just binary? What if they could use 3 states, or 4, or more? I mean, that's a question for the future of computing, for things like quantum machines, but it all starts with the simple yet powerful ideas we've explored today.